TRAX, Tracking in Complex Sensor Systems.
Hello, my name is Olga Isupova. I'm an early-stage researcher at the University of Sheffield in the UK, working on TRAX project. I would like to introduce the work of my colleagues and me about an application of an expectation maximization algorithm for behavior analysis in video. This work was presented on the International Conference on Information Fusion in Washington, D.C. in 2015. Nowadays, in video surveillance, human operators monitor screens to detect abnormal events like this guy crossing the road in the wrong place in order to react to these events. But human labor is expensive and exhausting. Moreover, the number of the cameras grows significantly every year, and soon it will be impossible to find humans to cover all this data. That is why we need some automatic tool to help human operators to detect abnormal events. There are a number of works in literature devoted to this problem. We can roughly classify them into two broad categories. This is pattern-based methods, where algorithms build behavior patterns and then compare a new observation with these predefined patterns. If the new observation is far away from any normal patterns or close to some abnormal ones, it is labeled as abnormal, otherwise as normal. The other category is statistical models, where algorithms seek for some statistical regularities within the data. This can be classical classifier, where we have labeled training dataset and train one class or two class classifiers to decide what is normal and what is abnormal. The next subcategory is probability distribution estimators, where algorithms estimate probability distribution of the visual data and calculate the likelihood of the new observation. If the likelihood is low, it is labeled as abnormal, otherwise as normal. I call them non-hierarchical just to distinguish with the next subcategory, topic models, where the framework is the same, but we have two levels of probability distribution. I will explain it in a moment. Now I just want to emphasize that in this work we focus on the statistical models and namely on topic models. Topic modeling was originally proposed for text mining, where we have unlabeled collection of text documents and we want to figure out what topics our documents are about. But topics are hidden variables, and we just assume that a topic is a distribution of words, and documents are a mixture of these topics. Here we have these two levels of probability distribution about which I mentioned earlier. Why do we choose topic modeling for abnormal behavior detection? There is a number of reasons for this. First, decision about abnormality is made within the probabilistic framework. It means we can use all power of the probability theory and statistic for our problem. Moreover, our decision is not binary. We have a confidence level of our decision. Topic model is not limited to be a tool just to decide what is normal and what is abnormal. It can also explain typical activities happening within the skin, helping us to understand what is going on. Topic model is a good base to add building blocks upon it to include our prior knowledge about the problem. If we want to apply topic modeling to video analytics, first we need to define what our words are and what our documents are. For words, we divide each frame into grid cell, and for each cell we calculate mean optical flow. We quantize this mean optical flow into 4 directions, like it is shown in the figure. The coordinates of the cell and the direction of its motion form our visual word. For documents, we divide the whole video sequence into non-overlapping video clips, 1 second length, and treat these clips as our documents. And this is our model. We have high level of abstraction called behaviors. These are different types of those topic mixture which I mentioned earlier. This behavior will explain everything within this clip. We can think about the behaviors as traffic light regimes if we have a fixed camera on a road junction. Each behavior corresponds to one regime. We model them to form a Markov chain, so each behavior lasts for some time and they change each other in the given order. The generative process is as follows. For each video clip, we firstly choose behavior. We choose it from the transition probability distribution matrix psi according to the behavior for the previous clip. Or if we are talking about the first clip, we choose behavior from the probability distribution vector pi. Once we choose behavior, the following procedure repeats for several times. We choose action or topic from the probability distribution matrix theta according to the chosen behavior. Once we choose the action, we finally choose a word which will express this action. We choose the word from the probability distribution matrix phi according to the chosen action. The only observed variables are visual words, and we would like to estimate the model parameters, which are the vector pi and matrices psi, theta, and phi. We estimate the parameters with the maximum likelihood approach using the expectation maximization algorithm. From our generative model, we can write down the full likelihood as it is shown on the slide. In the EM algorithm, we will iterate the E and M step, where on the E step we estimate the posterior probability of the hidden variables, and on the M step we estimate the model parameters with the values maximizing the expected value of the logarithm of the full likelihood. As we have Markov dependencies in our model, the inference on the E step is similar to the Baum-Welch forward-backward algorithm. We introduce the additional variables alpha and beta. They can be efficiently calculated via the recursive formula by the forward and backward run. Having the values for alphas and betas and the current estimates of the model parameters, we can calculate the required posterior probabilities of the hidden variables. This finishes the E step. On the M step, we estimate the model parameters with the help of the values calculated during the E step. Once we have the estimates of the model parameters, we can calculate the likelihood of a new clip with the help of these predictive behavior probabilities by this recursive formula. In order to compare clips with different lengths, we divide the likelihood to the clip's length. This is a summary algorithm for our method. During the learning stage, we iterate the E and M step of our EM algorithm, calculating the estimates of the model parameters. Then, during the testing stage, for each new clip, we calculate the predictive behavior probability and the normalized likelihood. If the likelihood is below the threshold, we label the clip as abnormal, otherwise as normal. We compare our method with the one proposed by Hospitalis and others. They have a similar generative model, but the inference scheme is based on Gibbs sampling. We compare the methods both on the synthetic and real data. We use two quality metrics for the comparison: the percentage of the errors and F measure, which is the harmonic mean of precision and recall. Precision is a fraction of model detections that are correct in terms of the ground truth, and recall is a fraction on the ground truth positive cases that are detected by the algorithm. This is our synthetic model. The lighter the elements, the higher probability it has. Imagine that we have a road junction with two perpendicular roads. We model the motion on the halves of each road as our actions. Behaviors models the whole motion. We have four types of motions: vertical and horizontal traffic flows, and two types of turns. The behavior dynamics as is shown in the figure. We generate 1000 training clips from these reference distributions according to our generative process. We use the uniform distribution for the initial behavior choice. Here we can see how the methods can restore the reference distributions. In this case, these are actions from the given training datasets. The first column corresponds to the reference actions. The other columns represent two independent runs for both algorithms. This is a similar comparison for behaviors. For testing clip, we generate 1000 additional clips, where we randomly included 300 abnormal ones. We have three types of abnormal clips. These are: first, abnormal joint word appearance, including new words, which were not in the training dataset. In this example, you can notice 3 new words. Second type of abnormality is joint action appearance. In the reference distribution, we set two different kinds of turns: from left to up, not to down, as in this abnormal case on the left, and from right to down, not to up, as in this abnormal case on the right. The actions themselves in this case are normal, but their joint appearance is abnormal, as within the training dataset we generate only other types of turns. Third type of abnormality is the abnormal behavior dynamics. It means that in the abnormal case, behavior appear in the order conflicted to the order given by the generative model. Like in this example, this turn should be followed by vertical flow, not horizontal. This is a quantitative comparison of the abnormality detection ability of both methods. We can see that our algorithm outperforms the one based on the Gibbs sampling inference. We then compare the methods on the real data. This is the University of Minnesota dataset for the detection of unusual crowd activities. It consists of 3 schemes, where the normal behavior top row is when people just walk around, and the abnormal behavior bottom row is when people run away from the scheme. This is a video of the results of our algorithm. On the bottom you can see the likelihood calculated by our algorithm. Here the example of abnormal behavior which is correctly detected by our algorithm. As we treat 1 second length clip as our documents, we have 1 second length delay just to collect the data, but the decision about abnormality is made almost immediately. There will be soon another example of abnormal behavior where people run away from the skin, which is also correctly detected by our algorithm. This is a quantitative comparison of both methods. We can see that ours outperform the one based on Gibbs sampling for all 3 skins. To sum up, we applied dynamic topic modeling for the abnormal behavior detection problem. We designed the new inference scheme for the model based on the maximum likelihood approach using the EM algorithm. We empirically showed that our methods outperform the one originally proposed for the similar generative model, but based on the Gibbs sampling inference scheme. Thank you for your attention. We would like to thank the support of the European Union Marie Curie TRAX project. Goodbye.
For more information about TRAX, please visit our site at trax.u20.nl.